Okay, so now that we understand a little bit more about the properties of acids and bases and acid and base strength, let's talk about the next idea here in acid-base chemistry, and that has to do with the ionization of water. So if you recall, we had a couple different definitions going on for acids and bases. An acid is either an H plus donor, according to Bronsted-Lowry, or something that gives rise to H plus or H3O plus ions in solution, in aqueous solution when dissolved in water. Bases were either proton acceptors by Bronsted-Lowry, or they would give rise to hydroxide ion, OH minus, in water. Now let's talk about the ionization of water itself. If you think of water, and especially if you consider it in terms of those Arrhenius definitions of acids and bases, water itself is an H plus and an OH minus that have come together to make H2O. So it stands to reason then maybe water can break up into H plus and OH minus as well. So that's what we'll push that concept here in this section of chapter 10. All right, so in the ionization of water, H plus is transferred from one H2O molecule to another. So one water molecule acts as an acid while the other acts as a base, right? One's a proton donor, the other's a proton receiver. Or if you want Arrhenius definitions, we end up with H plus and OH minus, or H3O plus in this case, and OH minus. So one of the water is an acid and the other water molecule is the base. And here we see that conjugate acid-base pair from the Bronsted-Lowry theory. Again, it's an equilibrium process, and this equilibrium lies almost all the way to the reverse. Very little of this goes forward. It's almost all as neutral water molecules, but a tiny, tiny little bit goes forward to make some H3O plus and OH minus aqueous ions in solution. When I say it goes only a very, very small extent forward, I'm not kidding. So the ion product constant, Kw, which if you remember we talked about Ka in the last section, Kw for water at 25 degrees Celsius is the product of how much of that water actually goes on to make H3O plus and OH minus, and it's obtained from the concentrations in pure water of 1.0 times 10 to the minus 7 molar at 25 degrees Celsius for both the concentration of H3O plus and OH minus, and that means when we multiply those together, we get 1 times 10 to the minus 14. So that's our Kw. It's a very, very small value because only a teeny, tiny little percentage, fraction of a percentage, I should say, of those water molecules actually go on to ionize. Most of the water stays as neutral water molecules. So as we just saw, in pure water, we get an equal amount of H3O plus and OH minus, because if one of the water molecules donates a proton, it's going to form an H3O plus on its neighbor, and it's going to be an OH minus. So we have to make them in equal amounts. It does change with temperature, so that's why it's important we specify 25 degrees Celsius for a Kw of 1 times 10 to the minus 14, but that's going to be always the case. If we have pure water, however much of it ionizes, it'll always ionize into equal amounts of H0 plus and OH minus, so we'll always stay neutral in terms of our overall pure water solution. If instead of a pure water sample, if we add an acid, that's going to cause an increase in the H3O plus concentration, and it's also going to cause a decrease in the OH minus concentration, and that'll cause the H3O plus to exceed that 1.0 times 10 to the minus 7 molar concentration. It'll cause the OH minus to become less than that 1.0 times 10 to the minus 7 molar concentration. So we have relatively more H3O plus and less OH minus, and that's characteristic of an acidic solution where H3O plus concentration is greater than OH minus concentration in a water-based acidic solution. So it stands to reason that a basic solution would be the opposite. So when we add a base to pure water, now we're going to increase the OH minus concentration. We'll also be decreasing the H3O plus concentration, and that's going to cause the OH minus concentration in that water to now exceed 1.0 times 10 to the minus 7 molar concentration, and it will cause the H3O plus concentration to be less than 1.0 times 10 to the minus 7. So there's that relationship that we're balancing out the H0 plus and OH minus in pure water, but then in acidic solution we have relatively more H0 plus, less OH minus, and now in basic solution we have relatively more OH minus, less H0 plus when we're dealing with water-based solutions. And here's a nice visual of that process. So right in the middle, we have the neutral solution, pure water, or neutral salts, things that don't act as acids or bases. We have H0 plus concentration equaling OH minus concentration, and at 25 degrees Celsius, they both equal that 10 times minus 7 molar concentration. If we look at our acidic solution on the left, now we have relatively higher H0 plus concentration, lower OH minus concentration, and that's characteristic of an acidic solution. Finally, on the right, we have our basic solution where we have the OH minus concentration greater than 1 times 10 to the minus 7 at 25 degrees Celsius, the H0 plus concentration less than 1 times 10 to the minus 7 at 25 degrees Celsius rather. Now, what I hope you picked up from that graphic is that as the 1 goes up, say H0 plus in the case of an acidic solution, the OH minus in that acidic solution goes down in a similar, although opposite fashion. Likewise, when we had our basic solution, the OH minus went up and the H0 plus went down in a related fashion. So the pure water is very easy to see that they're equal, but the interesting feature is that whether we're talking about neutral, acidic, or basic solutions, Kw at 25 degrees Celsius is a constant, right? It's the autoionization constant for water, Kw, and it's always 1.0 times 10 to the minus 14, whether we're talking about a neutral solution, an acidic solution, or a basic solution that's based on the solvent water. So this is a really neat feature. So we see neutral, we've already talked about that and it's easy to see. Acidic solutions, if we have a relatively high concentration of acid, something like 1.0 times 10 to the minus 2 molar concentration, well, that's 5-fold more concentrated, 5 orders of magnitude more concentrated than pure water. But look at the base. The base is 5-fold or 5 orders of magnitude less concentrated than pure water. And when we multiply those two together, we still get the Kw of 1.0 times 10 to the minus 14. And if we look at bases, the same sort of thing is happening. The basic solution, if we look at the second from the bottom, if our base is 1.0 times 10 to the minus 6, so 10 times more concentrated in OH minus than pure water, then look at our acid. It's 1/10 as concentrated as pure water, and we get that overall Kw value upheld. So this is really interesting and really useful information because now we can figure out not just for pure water that has equal amounts of H0 plus and OH minus concentration, but even for an acidic or a basic solution, if it's a water-based solution, we can figure out at 25 degrees Celsius the H0 plus OH minus concentrations based on Kw. Okay, it's the last chapter, so I think you've caught on by now that once we have something that allows for a calculation, we've got our guide to help us with calculating these values. So in this case, we're calculating H0 plus and OH minus. So first we would write the Kw for water. Then we could solve the Kw for the unknown, whether it's H0 plus or OH minus, or both if we have a neutral solution, but I wouldn't expect you to do that for an acidic or a basic solution. I would have to give you one or the other for a basic or acidic solution so you can find the missing species. Then finally substitute the known H0 plus or OH minus value into the equation and calculate. So let's go ahead and see how this works out now that we've talked about our guide. Okay, so here's our question. What is the H0 plus concentration of a solution if OH minus is 5.0 times 10 to the minus 8 molar? So based on that value, the OH minus concentration is less than the OH minus concentration of pure water, which is 1.0 times 10 to the minus 7. Now we're less than that, 5.0 times 10 to the minus 8. So we know that we're expecting an H0 plus concentration that's greater than 1.0 times 10 to the minus 7 if our OH minus is less than pure water. So first we'll write that Kw for water. Kw equals H0 plus concentration times OH minus concentration, which equals 1.0 times 10 to the minus 14 at 25 degrees Celsius. Step 2, we'll solve the Kw for the unknown concentration. In this case, it's the H0 concentration, H0 plus rather, that's unknown. And we'll solve for that by dividing both sides by OH minus concentration. In this case, we'll substitute in that known OH minus concentration, and then we can calculate the H0 plus concentration. And when we do that correctly, we see that we end up with 2.0 times 10 to the minus 7, which is indeed greater than 1.0 times 10 to the minus 7. That was our prediction based on the idea that the base is that this solution is less concentrated in OH minus than pure water, so this acidic solution must therefore be more concentrated in H0 plus, and indeed that was a good check to show that we did our work well when we found that it is 2.0 times 10 to the minus 7, twice the H0 plus concentration rather of pure water. All right, so this is not terribly taxing. You guys have been through much worse throughout the semester, so why don't we go ahead and confirm that you at least follow this relatively straightforward line of thought in maths by having you do a learning check. So in this learning check, you're asked if lemon juice has H0 plus concentration of 2 times 10 to the minus 3 molar, what is the OH minus concentration of that lemon juice solution? Again, it's an aqueous solution, so you can use the concepts we just used, and we'll assume we're at 25 degrees Celsius, so you can use the Kw value of 1 times 10 to the minus 14. So go ahead, pause the video here, select your answer choice, and we'll stop in and check your work once you start us back up. All right, so here we have it. Step 1, we'll write the Kw. As I said, we'll understand this to be at 25 degrees Celsius. So Kw equals H0 plus concentration times OH minus concentration, which equals 1.0 times 10 to the minus 14. We'll solve the Kw for that unknown. In this case, it's the OH minus that's our unknown concentration. So that's going to be determined by dividing both sides by H0 plus concentration to isolate the OH minus concentration. And finally, in step 3, we can substitute the known H0 plus concentration in and calculate the unknown OH minus concentration. Now here the lemon juice we know is acidic. It has a fairly high concentration of H0 plus, so we're going to expect a pretty low concentration of OH minus, certainly less than 1 times 10 to the minus 7. When we do the math, we find that we get a result of 5 times 10 to the minus 12 molar, and that means that our correct answer choice was choice C. So hopefully that's the answer choice you had selected and you had the work to back it up. If not, if you're struggling, if this is not a very straightforward calculation for you, please do try some others and certainly reach out for guidance if you're still having trouble. Again, it's not as involved as a lot of the other things, but if for any reason you're struggling, please do seek help. Otherwise, if things are going well, then we'll see each other again in the next section here of Chapter 10.